We introduced the definition of a basis, and we showed that every space could have infinitely many different bases. Why would you want different bases? What's the point? So a nice example of this are color models in image processing. On a digital screen, phone, or a computer monitor, they use what's called the RGB color model, red, green, blue. And they're essentially the analogy of the standard basis in R3. So if you want to take any color X, you represent it by some linear combination of those vectors. Now, the values of R, G, and B are integers between 0 and 255. So you might say, well, why would you want a different model? You might want to do what's called image processing. And in particular, you would like to do image compression. So we all view things on the internet, movies, images. They contain huge amounts of information in a single picture. What you would like to do is get a high quality image, but make the file as small as possible. So you would like to compress it while preserving quality. So you've likely all heard of JPEG file formats, what's called an image compression algorithm. It's based on a different color scheme. There's an alternate color model more closely related to human vision. This is what's called the YCBCR model. And we can think of this as another basis, V1, V2, V3. There's a number called the luminance that's significant when it comes to how humans see things. Other factors called blue chrominance and red chrominance. You could think of this Y vector, the first one, as some linear combination of the three colors R, G, and B. You could think of the second one as some other strange linear combination. Don't worry too much about these numbers. We won't really care. They're all found in the book. You've got a similar one in the other situation. What's important is that it's a different set of vectors. And the idea is that you want to be able to convert colors that are in the RGB into this YCBCR. When you are in this new basis, the Y really holds most of the information. So you want to preserve as much of this as you can, and then you want to eliminate as much of this as you can to compress the file. I would recommend that you take a look at chapter 3.3 in Austin to talk about this. How do we convert from one basis to another? Before we get to this, we need to introduce a new idea. So we need another definition. Now remember that when you are in a basis, there is a unique representation of any vector in your space, Rn. So if you have a basis for Rn, we've already discussed that by definition, it has to be a spanning set. So there have to be enough vectors to create anything, and it has to be independent. So you can't have too many. You don't want any duplicates. And that means that if you were to take any vector, form a matrix from these columns, it's going to be a square matrix. It's going to have a pivot in every row, a pivot in every column. So you will always get a unique answer to this question. And these numbers here are important. So we're going to make a definition. These weights, C1 all the way down to Cn. We are going to call these the coordinates of the vector x in the basis B. And we're going to give it a notation. X with these curly brackets and a B underneath tell you how much of each one of those vectors forms your particular vector. If I tell you that beta, B1, B2, B3 is a basis for R3, don't worry about what the vectors are. When I write 2, 1, negative 4, the vector x is formed by 2 bunches of B1, 1 bunch of B2, minus 4 bunches of B3. If I give you the standard basis vectors, so let's say E1, E2, if I tell you a vector x is just x and y, we've already seen that you could write it like this. X will have that many bunches of E1, and then we'll have y bunches of E2, and it's always the case that the vector x on its own is going to be equal to its representation in the standard basis. So we never bother putting these curly brackets with the standard basis because it's always understood that when you write a vector down without reference to coordinates, it's standard basis. But the real question that we want to answer is, if I give you this set of vectors xb, and I tell you, again, 2, 1, negative 4, what is this in standard basis? How do I convert between different bases? Put it a little bit more concretely, let's say I give you 2 separate vectors, 1, 1, negative 1, 1. You can easily show by putting this into a matrix that B is a basis for R2. If I tell you that the coordinate representation of a vector in this basis is 2, 0, this means that the vector x is formed by 2 bunches of B1 and 0 bunches of B2. You know what the basis representation is for each one of them. And that tells you you'll end up with the vector 2, 2. And this is what vector representation would be in standard basis. This vector x would be called 2, 0 in B basis, but in standard basis, it would be called 2, 2. So it's kind of like talking about the same object. You would name it something in French, but in English, it would have a different language. So the coordinates just tell you how much of each ingredient to get to a certain spot. There's also a nice geometric way of thinking of this. If you're just to take R2, there's the 0 vector. The standard basis vectors, we'll put them in green. E1 here, and you'd have 2 bunches of E1, and you could tick off all these different bunches of E1. You could have an E2, you could have 2 bunches, 3 bunches, etc. You can go for negatives as well. We end up making what's called a coordinate grid. Every multiple of our basis vectors, we put in these grid marks, just as a visual cue. And in this visual system, we create this. And our vector x, we were told, is the vector 2, 2. So in standard basis, we would go over 2 units in the green direction and 2 units up. In our B basis had 2 different basis vectors. B1 was here and B2 was there. And so what we could do is make a similar grid for the B basis, and we would get a different set of coordinates, and we could overlay the two kind of like this. The idea is there's a different way or a different set of instructions for us to be able to get to this point x. And it turned out that our vector was 2 bunches of this basis vector. So you can see that it's the same point in space, but it has different name depending on which language you pick. So if I want to do this in general, there's a very simple algebraic way to do it. If I have a basis, B1 all the way down to Bn, this is a basis for Rn. I can take any vector x that lives in Rn, and I can represent it in terms of this basis. I have all of these different weights that tell me how much of each basis vector to take. Now, by definition of a matrix vector product, I could write this as a matrix that holds the columns and then the weights that hold that information. The matrix that holds these basis vectors, I'm going to denote it with a C subscript B. And by our definition, this vector is the vector of coordinates of x in this basis. So we've got x is CB times this. This is a nice system of linear equations that connects the 2 different basis representation. So this system will allow us to convert from x, which is in standard basis, to B basis, and vice versa. What do you mean? You are always going to be given the basis vectors. So if I give you this system, the basis just forms the columns of that matrix. So the columns are basis vectors. That means this matrix can eventually be reduced to the identity, and that means that this matrix has an inverse. It exists. Don't actually form the inverse. If you are given this standard basis x and you want this xb, solve the system CB xb equals x. If you are given xb and you want just the regular vector x, it's just a matrix vector product. CB times that vector of coordinates is going to give you x. The textbook says use the inverse of this matrix. No, do not do it. Don't find the inverse. I'm going to give you 2 simple examples. So if I say to you a basis here is 1, -2, 5, -6, I would love to figure out the name of a vector in this new basis if I tell you that its name in standard basis is 4, 0. I have given you a dot on the plane, and I already know that the address in standard basis is 4 units to the right and 0 units up, but I would love to know how many of these 2 ingredients I would need to get to that same spot. So let's call this B1 and we'll call this B2. What I'm trying to do is form this linear combination. So that means I'm going to make a matrix times this column. This matrix is the matrix that holds my basis vectors. It's called the change of basis matrix, and I'm multiplying it by the coordinates here. That means I now have to solve this system. B1, B2 given x. 1, -2, 5, -6, 4, and a 0. If I row reduce this, I will end up with something like this, and it's pretty straightforward to see. It verifies a bunch of things. Yeah, it verifies that I do have a basis. C1 is -6 and C2 is 2. So this vector, which is 4, 0 in standard basis, could be formed by saying take -6 B1, 2 bunches of B2. Now if you want to check, -6 times 1, -2, 2 times 5, -6, and it will in fact give you that. As a final example to show you the other direction, if I tell you you've got this basis, -1, 2, 0, 3, -5, and 2, 4, -7, and 3, and I tell you that a vector is represented in this basis by -4, 8, -7, what is its representation in standard? Well, this just becomes a matrix vector product. You could take this matrix, multiply it by that set of coordinates, and just by definition of matrix vector product, you end up with this, and what you'll find, 0, 1, -5. So what we've got is a way to define any vector in terms of a magic set called a basis. We've got this idea of coordinates. Tell me how to use those given ingredients to get to a certain point. We can switch between bases using transition matrices.